the recording going here. So we did the first one last time. We got it into standard form, and then we went about the vertex and the axis intercepts. It's pretty good strategy to get it in the appropriate standard form first, and then go from there. It's really a matter of preference, though, I would say. So, because off the bat, you can pull a couple of things. You could pull the y-intercept. So the c value, I mentioned this last time, is the y-intercept. So the y-intercept here has to be equal to 0. Right? Again, and that's just matching this or stacking it up against the general form of a quadratic. If there's no c value there, that c value must have been 0. All right. So again, this is our y-intercept. So you could pull that right off the get-go, right? You could also get the roots, the x-intercepts. All right. So for the x-intercepts, you take your original function and set it equal to 0 and solve. Right. And in this case, it's not bad because you're looking at something that has a GCF, right? When you're solving quadratics, factoring, completing the square quadratic formula, all possibilities. But you don't start with the most difficult one. You go with what you deem to be the easier approach and go from there. All right. So in this case, I see a GCF. Now that GCF, I could look at it as 2x, but I also would like to get rid of those negatives. I like to have a nice clean leading coefficient. So I'm going to pull out a negative 2x. So we just want to divide each term by that GCF. You highlight everything. It's like you're highlighting nothing. All right. So start off with these two, and I'm going to get an x. Well, let me put the negative 2x in front. Apologies. All right, you're going to get an x. And then when you divide this term by negative 2x, you're going to get just a positive, plain old 2. No variable attached to it. So it's not bad because now I can take my two factors, negative 2x, set them equal to 0, and solve, and I'll have my x-intercepts. Right, so solve the first one, you get x equals 0. Second one, you get x equals negative 2. And now I have more points that I can plot on my graph, but I don't know where the vertex is. All right. And so I wouldn't want to start plotting stuff right away in order to, create the graph. I want to know what the vertex is before I get started on that, because if, what if I scale it wrong? Be doing a lot of erasing. All right. So for the vertex, or standard form gives us the vertex. There's other ways to get a vertex of a quadratic, but this is the way we're going to do it. I'm going to take my original function f of x is equal to negative 2x squared minus 4x. I'm going to apply the completing the square approach. All right, that's where we get rid of the c value. It's like, surprise, we don't have a c value here. That's great. That means there's nothing to get rid of. All right, but I will create the blank space and compute b squared over 4a. And I'll use a little color coding here. So my b value is right here. My a value is right here. So again, this is going right back to the original function, not any of the simplified versions of it that we came up with along the way. All right. So I'm looking at negative 4 squared over 4 times negative 2. So 16 up top, -8 on the bottom. That gives me a -2 as a result. And that's what's getting plugged into the gap, which really means I'm going to introduce a -2 to the right-hand side. And if I do that, I need to introduce a -2 to the left-hand side. Right. So I'm looking at f of x minus 2 is equal to all this stuff. Now we are dealing with a leading coefficient. It's not always the simplest thing to account for. The leading coefficient in previous problems was just a 1, or it, just disappeared when we were solving for the quadratic. But in this case, I need to maintain that. So what I'm going to do is I'm going to divide both sides of the equation by that leading coefficient. All right, so whatever this number is, we divide it out. On the left-hand side, I'm not actually going to do anything. I'm going to leave that as is. On the right-hand side, I'm going to carry out the division. All right, each term gets divided by a -2. So we'd be looking at x squared plus 2x plus 1. Really, when it comes to this completing the square approach, for these types of problems, we're really just moving things away from the trinomial to make the trinomial simpler to work with. And then we're just going to bring all that stuff back after the fact, right? Because now that it's nice and clean, this is the definition of a perfect square trinomial. So binomial squared. And get a fresh new color here. I'm going to take the square root of this term. It's going to go here. I already have some variant of that. Go like a reddish one. The square root of this term goes here, and we carry down the middle sign. All right, so those would be my factors. You could also write it as x plus 1, x plus 1, as a product, but it's more concise to write it this way. All right, now all that other stuff on the left-hand side is going to come along for the ride, but now I'm going to start bringing them back. All right, so I have that -2 there. So what I'm going to do is I'm going to multiply both sides by a -2. Cancels on the left. It's now introduced on the right. So now I'm looking at f of x minus 2 is equal to -2 x plus 1 squared. And then my last move there would be to get the f of x alone by adding a 2 to both sides. So f of x is equal to -2 paren x plus 1 squared plus 2. That's my standard form. And from the standard form, we get our 3 pieces of information that we talked about last class: the direction of the opening, the a value, whether it's positive or negative, and the vertex. All right, so the a value here is equal to -2. H and k values would be -1 and 2. That's my vertex. All right, and because the a value is negative, that means that this parabola is opening downwards. So now I have what I need to create the graph. I got x-intercept. Yeah.
Sorry, can you just explain how you got the h and k value?
So the formula for the standard form is f of x. Let me just move this down a little bit. F of x is equal to a paren x minus h squared plus k. So what we're doing is we're grabbing these two. And whether you reason it out or not, it's up to you. You could reason it out or you could do the math. But either way, you should come up with a -1, because what this is saying is 1 has to be the same thing as negative h, which means h has to be the same thing as -1. And then for the other part, these two things have to be the same, which means 2 has to be equal to k. HK makes the vertex, so I'm looking at -1, +2.
Okay, I see. Thank you.
No problem. All right, so now I just got to plot it. You know, you do all this stuff. I mean, it's a lot, but you do it all correctly, and the graph's going to work itself out. It does seem at this point like it's work for the sake of doing work, but there is value to this, and you'll see why down the line. But for now, it's like, couldn't I just got points from the calculator and plotted them? Why did I have to get all this stuff? There's more value in knowing how to get this stuff than getting just coordinates off of a calculator. All right, so I have a y-intercept of 0. I have x-intercept also of 0, so you know this thing's going through the origin. All right, I'm going to go out 2 units in either direction. That might be all I need, I'll see. But my other x-intercept is -2, so I know it's going to cross here. It's also going to cross, well, it'll have a vertex at -1, 2, which is right here. All right, so I have my intercepts. I have my turning point. I can do my rough sketch. Some people like to get a third, a third set of coordinates. Oops, that's terrible. In addition to x-intercepts, y-intercepts. I guess I could say fourth set of coordinates. Just to give a little better of an idea of shape. But I can tell you that in most cases, when we're creating a sketch of a graph, which is why we're learning how to do this, it's really for a sketch, not a precise point-by-point graph. Right? That's more numerical analysis. That's you do that in like a statistics class. Here, we just want to get a rough sense of where the graph is going, so that we have an idea of some important attributes, which we'll get to down the line. But having point-by-point precision, while it would be nice, it's not necessary for what we're doing. All right. So that's your capsule summary, your brief review of quadratics. And don't want to give it short shrift. It's just that when you're dealing with something that you spent maybe months working on in the past, in the college level, definitely weeks, you're like, wow, we kind of got through that really quickly. That's the nature of review. It's not for the point of dragging it out. It's just to remind you of the key characteristics of whatever we're talking about. Like, we'll get to exponentials down the line. You'll have seen that before. I'm not going to reteach everything that came before. I'm going to reteach the things that you need going forward. All right. So that's the moral of the story there. Talk about power and polynomial functions. And you know what? I neglected to mention this last time, but if you see decimal points in the title, those are the sections in OpenStax, the textbook, that correspond to the topic that I'm teaching. All right. So if you need more practice, you can go there. Let's see. Can we find h with a and b and then run h through the function to find k? Yeah, that's fine. The only reason that I did it this way is because it said specifically to write it in standard form. If it didn't say that, I would use my good old axis of symmetry formula and plug it all in. But But yeah, we're just kind of, it's one of those where it's like, we're only doing it this way because the question asked us to do it this way, right? What you might not know is that when we get to conic sections down the line, this technique is going to be absolutely necessary in order to handle some of those problems. All right, so that's third unit. So I'm kind of setting up, the slow burn here. All right. Now, power functions is a function that can be represented in the form of kx to the p power, where k and p are real numbers. K is known as the coefficient. That shouldn't be earth-shattering. The number in front of a variable is usually considered the coefficient. But the power is also a real number. That power can be a whole number. It could be a fraction. It could be a radical power. There's a lot of it could be negative, right? It's just got to be a real number. Didn't say rational number. So if technically you could have something like, for example, f of x is equal to ex to the pi power. All right. E and pi are irrational numbers. This one is about 2.718, Euler's number. And this one, yeah, should know this one, 3.14159, etc. Right, but that would technically be a power function. You could even look at the picture, take a look at the graph. I'll just put in something simple first, like x squared, power function. Now it's only a power function if it's a single termed expression. Coefficient is basically a definition of a monomial. Coefficient, variable, power. All right. Now, if I want to put in this newfangled one that I just created, I'll just put it in as y equals alpha y shift equals e. For numworks, I haven't quite figured out how to bring up just the letter e. My suspicion is you're always going to bring an e to a power and just delete the power. I'm not in love with that, but it's fine. Raised to the pi power. Lock it in. Graph. All right, the green one was the parabola. This funky orange one is the e to the x, ex to the pi power. All right, I can go back and turn one off. Yeah, that's if you want to hang on to it, get a better look here. You can navigate, go left, right, up, down. You get a little bit of a sense of what's going on. I mean, that looks like an exponential function. And in fact, it has exponential attributes to it. It's just, it is still technically a power function. All right, so I gave some examples below. Constant function. They're like, well, that's not coefficient variable power. Well, it is. It's got an assumed x to the 0th associated with it. All right. X, same deal, except it's got an assumed power of 1. All of these have coefficients of 1. This one, 1 over x, you're like, well, that's a fraction. That's not anywhere near what you just told us the definition was. But 1 over x could be thought of as x to the negative first power. Tuck a 1 in there, now it's a power function. All right. Same idea for the next one. This would be 1x to the negative second. X to the 1/2 power is the same as the square root with an understood coefficient of 1. You do the same thing with the cube root, 1x to the 1/3. All right. So they might be simplified, but they're all basically following the definition of a power function. Now, a polynomial function involves the sum and differences of power functions, right? So with a specific requirement that each distinct term would have a different power, right? Specifically, powers that are made up of whole numbers, right? So you're not going to see in a polynomial function, you're not going to see a fractional exponent or a negative exponent. That makes it a different type of function. In the case of polynomial, we're saying, for example, f of x is equal to 3x to the third plus 2x to the first, well, I'll go second here, plus 5x to the first plus 7x to the 0th. Right, but I'm just writing it in a simpler form. But you could also have a polynomial function like negative 17 minus 5x to the 14th power. It doesn't matter to the arrangement, ascending, descending order. It's just your powers have to be made up of whole number values. Right? Coefficients can't be equal to 0. But if they are, that just means that you have a term that doesn't, the power associated with that term is not part of the polynomial. So can't be equal to 0 and still be part of the polynomial. And that's all stuff that you've seen before, because most of the time when you're dealing with polynomials, you're talking about how do I go about simplifying? How do I get it to, instead of being a cubic function, how do I make it a product of a quadratic function and a linear function? Little things like that. All right. Coefficients. Well, we're going to be mostly interested with the degree and the leading coefficient of a polynomial function. The degree is the highest power in the polynomial. All right, so whatever the highest power is, that's your degree. All right, so this is degree 3. All right. Now, whatever the coefficient is that's associated with the term with the highest power, that's going to be your leading coefficient, even if it's not in the first position of the polynomial. So my leading coefficient is equal to -4. So you're finding the term with the highest power. That highest power is the degree. All right, so in the second one, the highest power I see is a 5. So degree 5. The leading coefficient, which I'm forevermore going to abbreviate LC, is the coefficient of the term with the highest power. All right, and the reason we need to know this is because how the first term of a polynomial behaves, the degree and the leading coefficient, it drives the ship. The rest of the polynomial is going to behave in that way. There'll be some variations for small values of x, but the more extreme values of x are actually going to behave the same way. Whether it's xt or p, it doesn't make a difference. It's the same idea. All right, so my highest power here is 3. So my degree, I'm looking at degree 3. And the coefficient associated with that term that has the highest power, the leading coefficient in this case, is going to be a -1. And I'll focus on the first one in terms of the graph. I'm going to pop that in. You know what? I'm just going to wipe this one out. I'm going to wipe them both out. I'm going to put in f of x is equal to 3 plus 2x squared minus 4x to the third. Okay. So I pop that in. That's my first function. Now I'm going to do the same thing. I'm going to add an element, but this time I'm going to put in just the leading coefficient. No, I'm sorry, not the leading coefficient, the leading term. So negative 4x to the third power. Lock that in. I put it in as f of x and change it to g of x because it needs to distinguish between the two functions. All right, that's just part of the programming. All right, so in number one, what I'm telling you is f of x is equal to 3 plus 2x squared minus 4x cubed behaves the same way, or the same as, I guess. I'm going to use y equals to distinguish. Y equals negative 4x cubed for large values of x. All right, so these two equations, both functions, this one and this one, they're going to have the same what we call end behavior, right? So for large values of x, whether it's in the positive or negative direction, right? So, you know, it's kind of hard to say for small values of x, large values of x in positive or negative direction. So I'm going to take a look at the graph here. And for this one, you could actually see that they sort of behave the same way regardless. It looks like it anyway. But let me change my my window here. See, they're kind of not really close. You know, they're in the same neighborhood. They have the same shape, but they're not physically in contact with one another. I'm going to change my axes and just go an ordinary negative 10 to 10. Confirm. Confirm. All right. So these are what the two graphs look like under, under a restriction of negative 10 to 10. But as we expand outward, and in fact, you can kind of see it. If I go to navigate, if I start working my way down the line here, you see the two curves start getting closer and closer to one another. It gets to a point where they're almost indistinguishable from one another. Right, so they weren't physically connected early on, but as we move further and further away from the y-axis, they become closer and closer to the point where you can kind of think of one as the asymptote for the other. All right, so it's kind of, if you think about it as like a function asymptote, you know, what curve are you going to get closer and closer to? You know, because you have things like vertical asymptotes and horizontal asymptotes, lines that you approach, but you could also have curves that you approach. Right. So in this case, when it was early on, yeah, that's going to take forever. When it was early on, they weren't connected, but as I move further and further away, they start merging with one another. And if they could actually ever get out to infinity, they would become the same curve. Right. And it really just has everything to do with whatever the term is with the highest power is going to increase or decrease at a faster rate than all the other terms of the polynomial. So it overtakes and just leaves the rest of the terms in the dust so that they have minimal to no impact on the shape of the distribution of points. All right, so that's a little bit on end behavior. Then we talk about the graphs of polynomial functions. And there's certain things that you need to know, and some things that, like, it's kind of nice to know this. All right. In the case of polynomials, because you have calculators, I feel like almost all of it falls in the realm of, hey, it's nice to know. It's really what you're going to be using this for down the line that makes all the difference. So that's why we have to learn it. But I try to streamline it as much as possible. This intermediate value theorem, I like to call it the common sense theorem. And it has everything to do with the fact that if you have a sense of how functions work, then this ends up being well, duh, of course this is the case. All right, so let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs. Now, something that people lose sight of this all the time because you get bogged down in the notation. When we have a set of coordinates, I'm just going to make a note here: x, comma, y, ordered pair. Like if I gave you an x followed by a y, you would know what to do with that. You'd plot that point, right? But if I tell you that y is a function of x, and that's the thing, you see y equals f of x, you're like, oh, okay, cool. Y and f of x are the same. This is saying, like when you see a word problem and you see the word is means equals. So I'm going the other way with it and saying y is a function of x. Then I can conclude that I have ordered pair x comma f of x. All right. So when the intermediate value theorem states that if f of a and f of b, what this is saying here is that you have some x value that we're going to call a. I'll actually do it a little bit differently. Let x be a. Then we end up with coordinates a comma f of a. All right. The notation, let's just put it this way. Without me explaining anything, if I just gave you this notation, you're like, okay, what are you doing here? But when I tell you that this f of a is the y value that you get when you plug a into f of x, that should make a little bit more sense, all right? Because anytime you have an x value that's a particular number, so like 2 or 10 or 14, and then you have a corresponding value of y, if you know that it's a function, then what you're really looking at is f of whatever the x value was that was given. All right. So for example, if I have x comma f of x, and then somebody tells me that x is equal to 2, then I'm looking at 2 comma f of 2. That's what we call evaluating a function, right? And specifically what that means is it's a set of instructions here. This is telling you, figure out, I can't write it. Yeah. Figure out the y when x is equal to 2. All right. People get bogged down with the function notation to the point where it gets in the way of them being able to understand anything else. All right. And so hopefully that was a little bit helpful. But what this is telling us is that when I see something like f of a or b, f of anything, it's just saying figure out what that y value is. Now, it might not be that simple if it's a complicated equation, or a function, but it should be something that at least gets you pointed in the right direction. All right. So for the first example here, given the function 3 plus 2x squared minus 4x cubed, determine f of 0 and f of 1. All right, that's along the lines of what I'm saying. So f of 0 is what you would get if you plugged a 0 into the function and use that to figure out what the y value would be at that location. It's going to give you a set of coordinates. All right. Now, 0 is a nice number when it comes to polynomials anyway. Everything except for the 3 canceled out. That's great. So what this means is f of 0 is equal to 3. That's the same as saying coordinate 0, 3. All right, so I have a coordinate 0, 3. I'm going to do the same thing with a 1. And just run through the 1. One is also a nice number, okay? Because this amounts to 3 plus 2 minus 4. So 5 minus 4 is 1. Again, that means that we're looking at f of 1 is equal to 1. And that's the same as saying coordinates 1, 1. Now, vocabulary, terminology, things like that, really important. So when the question asks, is there a 0 to the function? 0 is talking about x-intercept. I'll put a hyphen there. Oops. X-intercept, root, where it crosses the x-axis, whatever you like. All right. So what I want to know is, based off of these two coordinates, can I conclude that there's going to be an x-intercept somewhere between the x value of 0 and the x value of 1? And if you're not sure, do a quick sketch. Here's 0, 3. Here's 1, 1. All right. The intermediate value theorem states that if they have opposite signs, then there exists at least one value c for which the function is equal to 0, which is basically saying x-intercept. All right. So based off of what I have here, can we conclude that there's a 0 on the interval? The answer to that is, I don't know. This one's actually inconclusive because there's a bunch of different ways that I can get from the first point to the second one. I can do it like that. I can do it like that. Let's go, let's get a red here. It could be the case that I did some kind of wobbly movement and then came back up and grabbed it, in which case I might have more than one x-intercept. Well, I already used red. Go purple or whatever this color is. I'll keep it a little simpler. It could be something like this. Because I can't confirm that it must be the case that there's at least one x-intercept, I would say no, but it's possible. All right. We had no sign change there. It didn't go from positive to negative over that interval. Now, using the same function, we already know f of 1 is equal to 1. Just figure that out. I figure out f of 2. 3 plus 2 times 2 to the second power minus 4 times 2 to the third power. All right, and you can run the numbers on the side. You pop it into a calculator, whatever you want. All right. I was leaning back there, got a little too comfortable. So yeah, however you want to do it, bottom line is you just need to evaluate this. So this is a 3, we got an 8, 2 to the third is 8, times -4 is -32. So 11 minus 32, -21. Also, if you want, because we already have this function plugged in, you could go to the table and grab it that way. All right. Bottom line is, we now know f of 2 is equal to -21. So that means that I have coordinates 1, 1, coordinates 2, -21. I'd have to do some hellacious scaling here, but it is manageable. If I go, let's say, by tens, -10, -20, I could plot 1, 1. I'm going to bring it in, then I'll bring it out real quick. Say 1, 1 is right here. And then 2, -21, somewhere around here. If it's a continuous function, how am I getting from point A to point B without going through the x-axis? It's not like I can circle around it or anything. These two sets of axes are infinite. They go on forever. There's no circling around it. So if I have to, while also being a function, if I have to get from here to here, the only way I could do it is to go through the axis. Now I could wiggle around and get there eventually. That wouldn't be a function, but bottom line is, I say bottom line a lot, you got to go through the x-axis in order for it to happen. Must have x-intercept. All right. So we're looking at something where it's like, I could have just typed this in and looked at the graph and figured it out. Like, why do we have to do it this way? There are different schools of thought when it comes to that. And my default answer is, well, you'll need to know it for calculus. Sometimes that's true. Most of the time it's just a lie. I just say it to kind of, end the conversation, because when something's in the curriculum, we have to cover it. We don't have a choice. So it's like, I don't always want to say, well, it's in the curriculum, I have to do it. But all that aside, the whole, like, why do we have to learn this? Sometimes it's just nice to know certain things. Like, you really want to understand math, then you want to pay attention to the small details, not just what are the steps I follow to get the answer. I can tell you, I mean, this without any hesitation or doubt whatsoever. If your mentality in pre-calc is just tell me the steps so I can get it right, the hope is that you're not planning on doing much calculus, right? Because that approach isn't going to help you, right? I remember in high school, I had that mentality. I took pre-calculus, just followed the steps, didn't really think too much, didn't care to. When it was junior in high school, it's like, better things to think about, I guess. Then I got to calculus, and I knew how to do stuff. I knew how to get correct answers, but I had no idea why. Still was not in the mode of thinking. But then I went to college, and I said, you know what? I don't have the foundation that I need. If I really want to understand this stuff, I don't have the foundation. So let me go back to pre-calc, do that again, really understand why I'm doing what I'm doing. And then when I got to calculus, it all started clicking, so it's basically like one of those, it's always easier the second time around, which is not always true, even though the word always is in the saying. But it's in the neighborhood of like, do you want to understand, or do you want to just get it done, right? And everybody has different goals, but If you're in the neighborhood of, I really want to understand, then these little details along the way are really going to be helpful, like the intermediate value theorem. Right. I called it earlier the common sense theorem. If you looked at it and all this work that we just did and said, I don't see any how that's common sense. Like, what are you talking about? I can give you a quick demonstration using the same function, so nothing too crazy. But let's say I want to go from, let me just get it where I want to be. I'm going to calculate the zeros for this. All right. So the zero of this function, the purple one, pink, I'm not so good with the colors, but this point here has an x value of 1.109. Any point above that is going to have a positive y value. Any point below it is going to have a negative y value. But if I tell you, and let's see if I remember how to do this, I want to go to, let's say, just the x value of 1. That's a little bit above the x-axis. It's just a smidge before. You can see the y value, the f of x is equal to 1. All right. Then I go through the x-intercept. So let's say I go to 1.5. Oh, I put a decimal in there for no good reason. That now has a y value that's negative. The f of x is equal to -6. It transitioned from a positive y value to a negative y value. How do you get from a positive number to a negative number without hitting 0 along the way? Like, whether you actually state it is a different story. If I say, right, count from 10 and decrease incrementally until you get to -10. You might say 10, 9.5, 9, 8.2. Maybe you'll throw in a pi, a 1, then a -1, a -3, a -5. Somewhere between that +1 and -1, even though you didn't say it, you must have hit 0. You can't transition. There's no teleporting. You can't transition from a positive number to a negative or a negative to a positive without hitting 0 along the way. All right. That's the common sense part of it that I'm talking about. Because really, if you just think about it, it's one of those things where it's like, I can just look at it. I know it's going to be true. But if you're not, if you're not wired to think that way, then, nothing about this stuff will feel like common sense. Multiplicity, fun word. I mean, that's all I have to say about that. I mean, it's just a fun word. You say multiplicity, it's like you get people's attention, right? But when you're talking about polynomial functions, we have 3 types of multiplicity. One is a linear multiplicity, all right? So the behavior of a graph around the root will either be, and you could have multiple roots. Let me get my my shading in tool going on. Make it look nice, make it pop. Yeah, there we go. That's the good stuff. Now this one happens to have 2 roots, but we're just going to consider the behavior of the curve around the roots. All right. That would be this little window here. And this window here. All right. So if I really bring it in and look at it closely, it looks like, now it's not perfect, but it looks like in the neighborhood of that root, this is shaping up like a line. So it behaves like a line. Let me bring it out a little bit. That's multiplicity 1. All right, multiplicity 1. Now, again, fun word. But what that tells me is that this polynomial is behaving like a first degree polynomial, the one for first degree polynomial. All right. So I'm going to make a note of that. First degree polynomial. Polynomial. No, polynomial. All right. Now, you may not be trained to think of a line as a first degree polynomial, but I just give you an example of a line. You might have something like y equals f of x equals 2x plus 1. All right. We talked about this on the previous page. The degree is the highest power within the polynomial. All right. So this is a power of 1, which makes this a first degree polynomial. So because this is raised to the first power, it's a first degree. And it happens to be the case that it's a line, right? But the consistency there, the highest power, the degree, and the multiplicity should all have the same number. All right. But again, it's based off of what it behaves like at its roots. Sometimes the function behaves like around its roots, behaves the way it normally behaves. Right? A parabola is a U-shaped curve. Around the roots here, it also seems to be a U-shaped curve. All right. So it behaves like a parabola. Parabola, which is a second degree polynomial. All right, that's, you think about any quadratic equation, they'll have powers of 2. Right? So, or at least the highest power is power of 2. All right. So therefore, this is a multiplicity 2. All right. Now, if you see where this is going, that's great. But if you don't have much experience with cubic functions, you may not. So here, in the last one, I'm going to go light green for those keeping score at home. This one behaves like a cubic. And you know what? Behave. Behave will be the word of the day. All right. And so the word of the day is behave. So behaves like a cubic. All right, so just changing a setting here real quick. I'll write that down. Behaves like a cubic. Which is a third degree polynomial. And that means we're looking at multiplicity of 3. And I'll show you why that's helpful in a minute. But before I do that, I got to imagine that there's at least one person who probably would be me, where it's like, wait, cubic, I don't remember that. What's that again? So I'm going to just show you real quick the parent function of a cubic, which is just x to the third power. You know, cubic, the cube part of it, power of 3, right? It's not always the case in math, but sometimes the name of the thing tells you a little bit about the thing, right? So just looking at the graph, and I'll go auto. This is what a cubic looks like. All right. So it starts low, ends high, or starts high, ends low. All right. Depending on whether you negate it or not. But being able to recognize these things, and again, it's on the micro level, it's around the x-intercept. All right. So I have really kind of hairy looking notation there. Polynomial function is of the form of k times a factor times another factor times another factor, or so on. K is a constant multiplier. And then I throw in simpler everyday language. And it's not always simpler. It's just simpler than what came before it. We're looking for P of X, P for polynomial. It's a function of X where we're just saying it's polynomial. That's the standard way of representing a polynomial function. No, basically, actually any function, if you think about, like, ordinarily f of x would be the name of the function. But if you want to get more specific, think about the name of the function itself, like polynomial or rational, and just use that, the first letter of that word, in place of the f in f of x. So if I had a rational function, I'd say r of x. Right. So, it's a kind of a naming convention that people they sort of adhere to. It's not a requirement. It's just it helps people understand what you're trying to say to them. All right. So k times a bunch of factors raised to a power of either 1, 2, or 3. You're completely forgiven if you're like, well, that didn't help one bit. All right. So I'll show you a little bit more in a sec. All right. The reason why it's 1, 2, or 3 is because the 1, 2, or 3 comes from the multiplicity. Let me get rid of this. Multiplicity. All right. So I have a few examples here. And in most cases, I kind of have to give you some aspects of the graph. But the idea here is to be able to come up with the equation of the polynomial function that would produce this graph, when graphed. All right. So what I'm going to do is I'm going to pull the roots from the picture. I have a root here and here. All right. So the root, and again, vocabulary, terminology, really important. Anybody who talks math, they interchange between root 0 and x-intercept. All right. So it's not the kind of thing like I'm ever going to test you on, but we all speak that way. What are the roots? What are the zeros? What are the x-intercepts? It's not like I'm going to say, what are the roots? And by the way, that also means x-intercepts also means zeros. Like at some point, that's something that you're just going to want to know if you don't already. All right. But the root is -3 because we're looking at the x value of the coordinates at which it crosses the x-axis. This other one has a root of 2. Now, we can create factors from roots. I'm going to do a quick side problem real quick, redundant. Just off on the side here, I'm going to say, let's say, for example, you had x squared minus 4 equals 0, and you needed to solve it by factoring. All right, you'd factor the problem, x plus 2x minus 2. Equals 0. This would be your set of factors. Then you would take each of the two factors and set them equal to 0. And solve. These would be your roots. Right? There is a relationship between factors and roots where, if you don't want to do the approach I'm going to say, that relationship will save you some time, but I'm going to show you more explicitly. Because when I say that there's a root of x equals -3, I'm saying x is equal to -3. But if I want the factors, you'll notice prior to it being, just over in our side example here, prior to it being x equals -2, it was x plus 2 equals 0. This is where we want to get to, all right? So how do we do that? Well, instead of having -2 alone on the right-hand side, I want to have 0 alone on the right-hand side. So that's what I would do over here. I would add 3 to both sides. And you get x plus 3 is equal to 0. But if you I'm merging words right now. That's how late it's getting. If you notice the relationship between the root and the factor, you could save yourself the time, right? Because the root has a -3, or I'm sorry, the root is a -3. The factor has a 3 in it, but now it's the opposite sign, right? So instead of doing this work, which is totally fine, I can say, all right, it's going to be x. Well, -3 became +3, so I'm going to just go ahead and assume that +2 is going to become -2. I don't need the parens. All right, so this is the set of linear factors. So thinking about what we did over here, prior to having them separated, they were combined as a product of 2 factors set equal to 0. So I can now say x plus 3 times x minus 2 would be equal to 0, right? But if you have any experience with quadratics, you know that that's going to distribute out to a power of 2. And this don't look like a parabola. So we must be missing something. My arrows look terrible. I'm just going to take care of that real quick. I'll make it look a little, oh, that's my eraser. Right, and the thing we're missing is multiplicity. All right, it has to do with the behavior around the roots. All right, so around the first root, it's not perfect, but this looks like it's behaving like a line. So that would be a multiplicity of 1. So this is mult 1, which means that this gets a power of 1. All right, whatever the multiplicity is, it corresponds to the power of the polynomial, the binomial within the polynomial. All right, you get a little purplish thing going on here. This looks like it's behaving like a parabola. So that's multiplicity 2. So this gets a power of 2. All right, so now if I distributed it out, I'm going to end up with something that's raised to the 3rd power, but I have no idea what the coefficient is because I need to come up with the equation of the thing that will fit the points that I have on my paper. All right, so what we say is that we're going to have some polynomial function p of x that's equal to some coefficient that we don't know, and I'm going to call k, times x plus 3 to the first times x minus 2 to the second. All right, so we're a k away from having it. I just got to figure out what the k value is going to be. All right, and you notice in the picture, I have 3 coordinates given to you. We used 2 of them, but I ignored that last one. All right, and that's going to be the key to everything, because if I know that there's a coordinate 0, 1 is on the curve, what that means is that, this goes back to what I was talking about before, p of 0 must be equal to 1. And remember, I'm using p in place of f. The polynomial function, still a function, we still treat it the same way. All right. So, and you could also look at it this way by saying that this is the x value and this is the p of x value. All right. Becoming more familiar, more comfortable with the notation, it really goes a long way. All right. Like, it sounds dumb, but I can tell you, and actually, I'm kind of like, I'm not going to say I'm embarrassed of this, but because I don't get embarrassed. I know what my strengths and weaknesses are, and if it's a weakness area weakness, there's no point in getting embarrassed over it. But this is the closest close to being as embarrassed about something mathematically as I could possibly be, and that is about 8 years into my teaching career. So it's like 15 years ago. I still had no idea why it was important for an equation to be a function. Like, why do we care about functions? Why do we care about vertical line test? Things like that. Like, they've been kind of like force feeding me that over the years. And I'm like, is there any value in that? Like, why would I need to know that? And it has to do with predictability. So knowing that if you put one input into an equation, you'll get at most one output. That's really important. So if I were to say, for example, depending on the day, it's maybe I own a business. Like on day 10, I'm either going to have a profit of 10,000 or I'm going to be bankrupt. Like I don't want the or there. I want to know what's going to happen on day 10, depending on what has happened before. Right. So it's knowing that there's a single output given a particular input. Right. So when I put a 0 into this equation for X, I know that I'm going to get 1 as a result. It won't be anything else. All right. And that's going to allow me to pin down what the value of K could be. If P of X could be 5 different things, then K could be 5 different things. All right. That's that relationship. But knowing that it's a function allows us to pin it down to a single value. All right. So I'm going to go through and replace all of my X's with zeros. So P of 0 is equal to K times 0 plus 3 to the first. You don't really need to write the first. 0 minus 2 to the second. And since I know that P of 0 is equal to 1, that's this right here, I now know, or at least now have the ability to figure out K. Right? 0 plus 3 to the first power is 3. Negative 2 to the second is 4. So we're looking at 12K is equal to 1, which means that K has to be equal to 1 over 12. All right, so then we can backfill that into the polynomial. I now know that the value of K must be 1/12. So P of X is 1/12, X plus 3, X minus 2 squared. I used to make my students distribute this all out. A power of 2, power of 3, that's not too bad. But the next one's power of 4. It gets out of hand pretty quick. All right. So, but I do want to verify. Like I just did all this work. I don't want to make, I don't want to rely on faith. I want to make sure that I got something that's going to go through the points they gave me. All right. So I'm going to go to my expressions tab here. I guess it doesn't matter because I'm going to write it as binomials anyway. 1/12. Beauty of this calculator, when you put a division, it makes it a fraction. And if it's not something that's easily represented as a fraction, it gives you a decimal approximate. X plus 3, X minus 2 squared. Lock it in. You can look at the graph, but the table is really where I want to focus my attention. But I'll bring up the graph real quick. Yeah, it kind of looks the same. It's in the same neighborhood, but unless I want to test point by point, that could be problematic. I'm just going to go on up to table. And just make sure that the points they gave us are in the table. All right, so -3, 0. Yep. 0, 1. Also, yep. And calculators do this from time to time. It's really aggravating, but it all depends on the tolerance that's available in the computing. Sometimes it'll give you this number. It's begging you to say, you know what, I get what you're saying. That's 0. Right? Because this is the equivalent of 0.000000000000000000111. It's trying to say 0. All right, but it's not very satisfying. That's just how the calculating technology works. Same thing with the TI-84. It'll spit out a number like that, and you'll be like, okay, so you're writing 2.9999999. Why not just say 3? It's just it's beyond its capability for that particular computation. All right. Now, B, look at this bad boy. Got a lot of stuff going on here. We have 4 roots, but they all have a linear affect. There's no wiggle as it goes through the x-axis. So I'm looking at 4 distinct roots, all with multiplicity 1. All roots mult 1. And again, what I was saying before is you pick out the shortcut instead of, oh, that's the wrong one. Instead of saying x equals 2, x equals 5, and then coming up with the factors that way, we can just jump right to the corresponding factors by reversing the sign. So I would say x plus 3 nice. X plus 3, x plus 1, x minus 2, x minus 5. Now, this is all going to be part of a polynomial function, p of x. We just don't know what the leading coefficient is supposed to be. So p of x is equal to k times a bunch of factors, like I said on the previous page. They gave us an additional coordinate, 0, 7. 0, 7 tells me that if I take, with an F there, a 0, plug it in for x, it should spit out a 7. All right, so everywhere I have an x, I'm going to replace it with a 0. P of 0, k times 0 plus 3, 0 plus 1, 0 minus 2, 0 minus 5. All right, all the same 0, all coming from this. Now that P of 0 on the left-hand side, stated right here, given by the coordinates and our understanding of function notation, this left-hand side is equal to 7. So now I could say that this is k times 3 times a 1 times a -2 times a -5. 0 is a great number. And from there, I can simplify, clean it up, and come up with my polynomial function. So we're looking at 30k is equal to 7, which means k, if I divide both sides by 30, is going to be 7 over 30. And now I could backfill that into the polynomial, or polynomial function, I should say. So P of x is equal to my new k value, new and improved, multiplied by a bunch of factors, the same bunch of factors that came before. And that would be my polynomial function. And that, if you put it into a calculator, would produce this graph. All right. The last one here, I'm going to put a star on. So just like last time, put a star on a problem. have you take a look at it, and we'll start off class next time with that. I made a little note, assume 3, -120 is a point on the curve, just because if you look at the scaling here, it's pretty rough. All right. And 3 would be off the grid anyway. So I'm saying that if you were to go down forever, somewhere along the lines, you'd have 3, -120 on the graph. All right. So you're just going to make that assumption. But this piece of information here is going to help you figure out the K. All right. So you go through, you identify your roots, come up with the factors, the multiplicity, pop in the coordinates, solve for K, and go from there. All right. So yeah, definitely want to practice with that. Going the other way isn't really that terrible. Like if you have a polynomial and you need to come up with a graph, it's a little bit easier. We use the calculator a lot for that. But when you're given a pre-printed graph and you need to come up with the equation, it's not the easiest thing in the world unless you follow this technique. In which case, it's still not the easiest thing in the world, but it's a lot easier than it would be. All right. So keep sliding down in my seat. I am going to stop the recording.